Continuing on our discussion, our lecture for today is potential energy. So the gravitational potential energy, which is denoted as PE, potential energy, is the energy that an object of mass m has by virtue of its position relative to the surface of the Earth. That position is measured by the height h of the object relative to an arbitrary zero level. So the formula for potential energy is mass multiplied by acceleration due to gravity and its height. So the SI unit of potential energy is joule. So work, kinetic energy, and potential energy have the same unit, joule. Okay. So let's have this illustration problem number 7.1. A gymnast springs vertically upward from a trampoline, as shown in figure 7.1. The gymnast leaves the trampoline at a height of 1.20 meters and reaches a maximum height of 4.8 meters before falling back down. All heights are measured with respect to the ground. So, ignoring air resistance, determine the initial speed v sub I with which the gymnast leaves the trampoline. So, based from the given figure, so all measurements, okay, uh, of the height are measured from the ground level. So, initial height up to the perhaps the trampoline, okay, and then its final height or final position to its feet is given 4.8 meters and initial height is 1.20. Okay, so upon reaching the maximum height of the person or the gymnast has a final velocity of 0. Okay, so speed, initial velocity, speed is unknown. Okay, so v sub o based on the figure. So solution, since only gravitational force acts on the gymnast in the air, it is the net force, and we can evaluate the work by using the relation. Work done with respect to gravity will be equal to the formula mg h. H is the uh, difference between the initial and the final height. Okay, now given initial height is 1.20, the final height is 4.80, and final velocity is 0. So we can use the work energy theorem. Okay, work energy theorem. So work energy theorem is equivalent to change in kinetic energy. Remember or recall formula for kinetic energy. Kinetic energy is equivalent to 1/2 mv squared, right? Okay, so the kinetic energy final and minus the initial kinetic energy. So final kinetic energy gives you a velocity of 0 at final position. So this leads to 0 velocity. So 1/2 multiplied by its mass multiplied by 0 gives you 0. Okay, minus initial kinetic energy. So we could say that the work done is negative initial kinetic energy. Okay, but then since gravitational force is only applied, okay, so work based on gravity will be equal to the negative initial kinetic energy, where work done by the gravitational force is equivalent to mg initial height minus final height. Okay, so substituting the formula for kinetic energy, so 1/2 mv squared, which is initial, so initial speed squared, and substituting the given, okay, 1.20 for initial, 4.80 for the final height, and then mass can be eliminated by dividing both sides by mass. Okay, so solving for the initial speed gives you a formula of so multiply both sides by 2. Okay, so 2g h of o minus hf and vi squared negative. So dividing both sides by -1 gives you this equation. Then square root both sides gives you this value. And substituting all the given, so -2g, which is 9.81, h of o is 1.20, and final height is 4.80. So the initial velocity is 8.4 meter per second. So conservative versus non-conservative forces. So when we say conservative forces, these are the forces that has gravitational force, elastic spring, or electric force. And when we say non-conservative forces, these are static and kinetic frictional force, air resistance, tension, normal force, propulsion of a force of a rocket. Take note that the concept of potential energy is not defined for a non-conservative force. Conservation of mechanical energy. So this concept work and the work energy theorem have led us to a conclusion that an object can possess two kinds of energy, kinetic energy and gravitational potential energy, PE. So KE and PE, or kinetic energy, potential energy. So the sum of these two energies is called the total mechanical uh, energy, denoted as E. Okay, so that the total mechanical energy is equivalent to the sum of these two energies, which is the sum of kinetic and potential energy. So the concept of total mechanical energy will be extremely useful in describing motion of objects. Okay, so the total mechanical energy, which is this one, okay, of an object remains constant as the object moves, provided that the net work done by external conservative forces is zero. Okay, so the external conservative forces is zero. This means that uh, they are not included in the equation. Okay, so what are these external non-conservative forces? These are the frictional force, normal force, and so on. Okay, so the formula for net work done by the non-conservative forces, okay, this is the net work done by the non-conservative forces, will be equal to the final total mechanical energy minus the initial total energy. So when net work done by the by the external non-conservative forces is equivalent to zero, so that becomes zero will be equal to final mechanical energy minus initial mechanical energy, and this becomes this equation. Okay, so from this equation we have since this is final, recall that mechanical energy is equivalent to the kinetic energy plus potential energy. So the equation becomes for final mechanical energy, so that is kinetic energy final plus potential energy final will be equal to kinetic energy initial plus potential energy initial. Substituting the formulas of kinetic energy and potential energy, this gives you kinetic energy is 1/2 mv squared, since it's final speed or velocity. Okay, so age at final position, 1/2 mvi initial speed plus mghi or initial height. Okay, so this can be used, this formula. Okay, so let us see this given problem. So illustration 7.2. Okay, uh, a motorcyclist is trying to leap across the canyon shown in figure 7.2. So this is the motorcyclist, so trying to leap across the canyon. Okay, so driving horizontal off the cliff at a speed of 38 meter per second, ignoring air resistance. Find the speed with which the cycle strikes the ground on the other side. So upon leaping, okay, with initial velocity of 38 meters per second, okay, what will be its final velocity or final speed? Okay, upon striking the ground on the other side. Okay, so solution: since air resistance is being ignored, okay, the net work done by external conservative forces is 0. So 0 will be equal to E sub f minus E sub I. Okay, so that will give us this equation. So from that equation, this is the final mechanical energy will be equal to initial mechanical energy, and our formula is this one. Okay, so kinetic energy final plus potential energy final will be equal to kinetic energy at initial and potential energy initial. Okay, so based on this equation, okay, uh, both sides or every term has a mass m, okay, of the rider. So this can be eliminated from this equation, factoring both sides by m, okay, dividing both sides by m eliminates m, and this gives us 1/2 v sub f squared, okay, plus mgh, which is ghf, okay, we divide m, and b sub I and ghI. Okay, then solving for the final speed, okay, this one. So this term can be transposed and becomes negative, so minus g h f, okay, and multiplying the whole term or both sides by 2. Okay, so if I multiply 2 here, so 2 multiplied by 1/2 is 1, so v sub I squared, then 2 ghi plus 2 ghf. Okay, so 2g 2g, they have both 2g, so factoring 2g, so this gives us this equation. Okay, so v sub f or final speed squared will be equal to initial speed squared plus 2g, then product of initial height minus final height, and squaring both sides gives you this equation. Okay, now substituting the values given, so initial speed is 38, acceleration due to gravity is 9.81, initial height is 70, okay, and the final height is 35. So 38 squared plus 2, 9.81, then 70 minus 35, and using your calculator you'll have a final speed of 46.16 meters per second. So that is the speed of this motorcyclist upon striking the ground on the other side. So next problem, illustration 7.3. The king the K is a giant among roller coasters. So as shown in figure, roller coaster. Located in Jackson Township, New Jersey, the ride includes a vertical drop of 127 meters. Suppose that the coaster has a speed of 6 meters per second at the top of the drop. Neglect friction and air resistance and find the speed of the riders at the bottom. Okay, uh, I'll assume, okay, the initial position, okay, a vertical drop. So vertical drop of 127. So let's say this is 127 meters. Okay, not reaching the ground. So initial position up to the ground. Okay, so let's say this is HO or HI. Okay, and let's say this one. Okay, and then up to the ground, its final position. Okay, final height up to the ground. Okay, so you can say that HI minus HF will be equal to 127 meters. Okay, so suppose that the speed, okay, so let's say this is the initial speed, will be equal to 6 meters per second. So what will be the speed at the final? Okay, that will be the question. Okay, now so this for problem is similar to the previous problem. So since air resistance and friction, okay, are being ignored, that's the work done on by the external conservative forces will be equal to 0. Okay, so this is 0. So if this is 0, we can say that the final mechanical energy will be equal to the initial mechanical energy, giving you this formula. And similarly, mass of the rider can be eliminated by dividing both sides of each term with the value of m. Okay, okay, so gives you this formula. So then solving for the final speed, okay, leads you to this equation. So v of f squared will be equal to the initial squared plus 2g and h of I initial minus final. Okay, so taking the square root of both sides. Okay, and then substituting the values. So the final velocity will be the square root of initial velocity 6 squared plus 2 times initial I acceleration due to gravity, which is 9.81, multiplied by initial position or initial height minus the final height, which gives us 127 meters. And using your calculator, we have an answer of final velocity of 50.28 meters per second. So problems 7.3 and 7.2, the previous example, are similar, are having similar approach in solving the problem. Okay, now let's deal with non-conservative forces and the work energy theorem. So non-conservative forces, what was the note again? Non-conservative forces. Okay, so non-conservative forces, okay, the concept of potential energy is not defined for a non-conservative forces. So that is why we will be using non-conservative forces with the help of the work energy theorem. Okay, so most moving objects experience non-conservative forces. Example, air resistance, okay, friction, and propulsive forces. So the work done by the net external conservative forces is not equal to 0. So we are considering now friction, air resistance, repulsive forces, or simply the non-conservative forces. So okay, so the work net work done by the net external conservative forces will be equal to the final mechanical energy minus initial mechanical energy. And solving for the final mechanical energy, that gives us initial plus the net work done by the conservative forces. Okay, let us try this illustrative problem. So 7.4. So referring to illustration 7.3, so the previous problem, we ignored non-conservative forces such as friction. Okay. In reality, however, such forces are present when the roller coaster descends. So the actual speed of the riders at the bottom is 45 meter per second, which is less than the determined in illustration 7.3. So this is however the actual speed of the rider at the bottom, or the final speed at the bottom, which is we have solved is much greater than this value. Okay, so assuming again that the coaster has a speed of 6 meters at the top, find the work done by the non-conservative forces on a 50 kilogram rider during the descent of the height initial height to height of final, where h of O minus h of F is equivalent to 127 meters. Okay, so since the external forces or non-conservative forces are being considered, so the net work done will not be equal to 0. Okay, so this is now has a value. Okay, which means this is not equal to 0. So the net work done will be equal to initial minus final minus initial mechanical energy. So mechanical energy is equivalent to kinetic energy plus potential energy. So since this is final, so velocity at final and height at final position minus 1/2 mv sub I squared plus mgh. So the question is find the work done with external forces. Okay, so factoring out, okay, so combining the kinetic and potential energy, so 1/2 mv squared, or 1/2 mv final minus 1/2 mv initial squared. So, okay, and minus mghi minus hf. Okay, then substituting the values, we have 1/2 mass is 55. Okay, 55 kilograms. Then final velocity or speed is 45 meters per second squared. Then minus 6 meter per second then squared. Okay, minus m base mass is 55, g is 9.81. Then h of I minus h of f is 127 meters. Okay, so solving for the work net external conservative force gives you non-conservative force gives you a negative 13,825.35 joules, or this can also be written as negative 13.825 kilo joules. Let's say R. Okay, so when conservative forces are being considered, okay, this value is not equal to 0. Illustration 7.5. Okay, a 0.20 kilogram rocket in a fireworks display is launched from rest and follows an erratic flight path to reach the point P, as shown in figure 7.4. So at initial position, then an erratic path, okay, then at point P with final speed. So point P is 29 meters above the starting point, okay, so 29 meters. So in the process, 425 joules of work is done on the rocket by the non-conservative forces generated by the burning propellant. Ignoring air resistance and the mass loss due to the burning propellant, find the speed of the rocket at point P, or the final speed at point P. Okay? So since non-conservative force is considered, and the only non-conservative force acting on the rocket is on the propellant. Okay, so the net non-conservative force on the propellant is 425 joules. So from the work energy theorem, okay, net work done by the non-conservative force will be equal to the change in mechanical energy. So this gives us this formula, okay, so kinetic at final plus potential final minus, okay, kinetic initial plus potential initial. Okay, so solving this expression for final speed of the rocket, for final speed of the rocket is v sub f. Solving for v sub f using this equation gives you this equation. So final velocity speed will be equal to the square root of twice the non-conservative force plus kinetic energy initial minus mg height at final minus initial all over mass. Okay, so substituting the values, so we have non-conservative force network is 425, so 1/2, mass is 0.20, initial velocity is given 0, okay, squared, minus mass, acceleration due to gravity is 9.81, and hf minus ho or hi is 29 meters, divided by 0.20 mass. Okay, so the final speed of the rocket at point P is 60.67 meter per second.